Hello everybody. In today's lecture we are going to be talking about the naming of different ionic compounds and how to go from a formula to the name of the compound. So in order to do that we're going to need our understanding of what we talked about in class on Thursday or on Tuesday of last week, where we talked about the ions and how each element can form a different number of ions based on how many electrons it either gives up or how many electrons it absorbs. So let's first see why we want to be able to name formulas properly. And then tomorrow in class, we're going to go from the name of the compound to the formula. So today we're going to work at the forward direction, and tomorrow in class we're going to work it in the reverse direction. So first off, let's see why the chemical formula is so important. So a chemical formula consists of the elemental symbols with numerical subscripts. We've all seen this before. Water, it has H, the symbol, the atomic symbol for hydrogen, a subscript 2, and then an O. And so each one of those means something. We know already from our AZX notation that H stands for hydrogen and O stands for oxygen, but what does that 2 mean down at the bottom? So let's learn about that. The chemical formula indicates the type and number of each atom that's present. So that's what that subscript means for that H2O. The 2 in the subscript actually stands for there are 2 hydrogens in one water molecule. And the chemical formula is in the smallest unit of the substance. So water, you can't have H4O2 for water. You have to have it reduced to its lowest form, which is H2O. So of course I just gave away the punchline before I showed you it. Here let's look at this water molecule. We know that this is the molecular formula for water. It has capital H for hydrogen, subscript 2, that means that there are 2 hydrogens, and then a capital O. We as chemists, as I've said before, are pretty lazy in the way that we write our number 1. Here, there is really a 1 as a subscript for that oxygen, but we don't write it. It's one extra pen mark that we don't have to write. So here, there are 2 hydrogens, and there's 1 oxygen atom. So this is an important feature of a chemical formula. When we get into stoichiometry, which we're going to be coming up in a few weeks, next week, we will be learning how to convert from grams of a material or a compound into atoms of each of those elements. So we're going to be using this molecular formula in order to do that. So let's see how we name these. We're going to first start off with the main group metals. Remember, we're going to be taking the new school name of naming, this new school way of naming, where we have 1A all the way through 8A. So we're going to skip those transition metals for right now. But in order for us to have an ionic bond, we saw this in class on Tuesday of last week, the metal is going to be giving up an electron, and the nonmetal is going to be absorbing an electron. So anytime we write the formula for an ionic compound, for these binary ionic compounds, the cation is going to be written first, and the anion is going to be written second. Now remember, the cation is the element that gave up the electrons, and it's in general going to be the metal. So we have the left-hand side of the periodic table, those are going to be your cations. The anion is going to be your element that absorbed the electron. So that's going to be on the right-hand side of the periodic table, those are your nonmetals. So a binary ionic compound is a compound between 2 elements, one a metal and the other one a nonmetal. So in the binary ionic compound, both the cation and anion are monatomic. What that means is we're only taking one element that's a cation and one element that's an anion. We will later on the next video talk about polyatomic ions, which means that we can have many different atoms or elements in one compound. But here we're only talking about 2. So let's see. The name of the cation in this case stays the same. So if we have a sodium in a chemical formula, chemical compound, we don't change the name of sodium. It remains sodium. So we can probably see this from sodium chloride. The way I just said it, sodium, we didn't do anything to the sodium. The anion changes, however. So for sodium chloride, we know that Chloride is not found on the periodic table. Chlorine is found on the periodic table. And so what we do for the anion in the case of the binary ionic compounds is we take the ending away from the anion and replace it with "ide" or IDE. In this case, there are no prefixes. When we start talking about covalently bonded systems, we will talk about prefixes. But here, there are no prefixes in binary ionic compounds. So these are the elements that we're going to be associating with for this first part of this video. So here are our main group elements, 1A all the way up through 8A. We're never going to be bonding one of these noble gases to anything. We can technically bond it right now, but it's a little bit more advanced than our class. So we're not even going to talk about this group 8A. We're just going to remain focused on 1A through 7A. So here, if you remember on Tuesday of last week, we had talked about that all the group 1 metals, main group metals, take a +1 charge. All the group 2 metals take a +2 charge. All the group 3 metals take a +3 charge. 4 metals, once you get down lower on the periodic table, they can start taking more, a number of different charges when they form ions. But we're going to mainly stay with these group 3s all the way through group 1 for the main group metals. For the nonmetals, in order to find the charge, we need to take the group number, in this case, if we were talking about nitrogen, 5A, and subtract 8 from it. And so in this case, 5 minus 8 is -3, and you see nitrogen takes a -3 charge. Oxygen here is in the 6th group, so it would be 6 minus 8 is -2, and here we have oxygen is a -2 charge. These are going to be the charges that we're going to be associating with our nonmetals. There are some other nonmetals here that are not shown. They have special properties. They're really close to these metalloid series, so they can kind of take different charges on them. So we're not going to be really focusing on these ones at all in this class. In Chem 1510, we'll be able to walk through it a little bit more in detail. So here's a list of all of our common monatomic ions. These are our group 1 metals, our group 2 metals, and our group 3 metals. The ones in silver are actually your the ones in red are your transition metals. Silver is a transition metal, zinc is a transition metal. Aluminum should not be written in red in this case. It's actually a main group metal, so it should be written in black, but on this table it ended up being in red. Do not memorize these charges on silver or zinc. We're going to be talking about this a little bit later on in the video, so don't worry about those. The ones written in black and aluminum, those are the ones that you should become familiar with. Here are our anions. So these are all of the cations on the left. These are all of the anions. If you notice all of the halogens, remember group 7A, they're called halogens, and they all take a -1 charge. The next group over to the left, group 6, is going to take a -2 charge, and the next group over, starting with nitrogen, is going to be your group 5, is starting with nitrogen, is going to be your -3s. What I've done here, or what the textbook has done here, is it has shown you how to write the anion's name in a formula. So we know that fluoride does not exist on the periodic table. It comes as fluorine. And so that ene part, we're going to drop that off and make it an ide. Chlorine is found on the periodic table, but written in a formula, it's chloride, and so on. So these are going to be all your anions you're going to be dealing with when talking about binary ionic compounds, and these are going to be all of your cations for the main group metals to nonmetals. Let's take a few examples. NaCl. So this is the formula. Tomorrow in class we're going to learn how to write this formula, but for now we're just going to be able to go from the formula to the name. So the metal, the cation, it stays the same. So we know we can look up on the periodic table, Na, it stands for sodium, so that is our cation. We don't change the name of the cation. So in this case, it's just sodium. For the anion, the Cl, we're going to be dropping the ending of Cl, of the chlorine, the ene part, and we're going to add ide to it. So this is our nonmetal. Our chlorines are nonmetal. It's also our anion in this case. So instead of chlorine, we're going to drop it off and be chloride. So chlorine, we drop off the INE part, and we make it IDE. So now we've gone from chlorine to chloride. In order to put this all together, all we do is name the cation and then the anion with the modified ending. So this is going to be sodium chloride. Pretty easy. Going from the main group metals bonding to the nonmetals, you don't really change a whole lot. It's just the metal's name and then the modified ending of your nonmetal. Let's try another example. Al2O3, tomorrow in class we'll learn how to write this formula, but for now just trust me, this is the formula for the compound. The metal is our cation. It's always written first. So aluminum, Al, was written first. It's our cation. We don't change it. It's still aluminum. Our nonmetal is oxygen. And in this case, we're going to drop off a whole bunch of the ending for oxygen and make it oxide. So chlorine, a lot of the endings of cations or of anions are -ine, so that's really easy to drop it off. But oxygen has a different ending. So we're just going to take the first two letters, ox, and add I to it. So this oxygen becomes oxide. So in order to name this formula, we just say our metal and then our nonmetal. So it's aluminum oxide. Pretty simple. So that's for the naming of binary ionic compounds from the main group metals to the nonmetals. Now what happens when we have transition metals? Well, the main group metals will always take that specific charge. So the group 1s always take a +1. The groups 2 always take a +2. The transition metals are a little bit different. They can take multiple charges given what situation they're in. So they're a little bit more difficult to pinpoint. So for now, I'm going to show you the formulas and I'm going to tell you what the charge is on that cation. Tomorrow in class, we're going to be learning how to back calculate out of the formula what the charge is. So let's learn about the naming from the formula to the name. Same thing as our binary ionic compound between the main group metals and nonmetals. With the transition metal, we don't change the name of the cation. So if we're talking about chromium, it's just going to remain chromium. However, since the chromium metal, the cation, can take many different charges, we have to denote exactly what charge is on that element. So let's see, we're going to be using Roman numerals in order to do this. And what that means is if this was a chromium with a 2+ charge, we would write chromium and then 2 lines to indicate that it is a 2. So that would read chromium 2. And then of course for the anions, we use the same endings that we did before, where we modified the ending and add I to it. So let's get to an example. How do we use these Roman numerals? What do they look like? If you don't know how to write Roman numerals, I suggest learning how. We're going to be using Roman numerals a lot for the rest of for the remainder of the course. So Roman numerals become key the later we go on in chemistry. So here are our transition metals. A lot of these are not marked in. The ones that are, these are the common charges that the transition metals take in these cases. And here's chromium. If you see here, we have chromium with a 2+ and we have chromium with a 3+. What that means is chromium could take either a 2+ or a 3+ when it's bonding. So we have to denote exactly in the name, we have to denote exactly which charge this is. So this would be chromium 2, 2 lines. This would be chromium 3, 3 lines. Manganese, this one has only one common ion. You still have to write the 2, so you write manganese 1, 2, 2 lines. But in most cases, this is only going to bond as a 2+ charge. Some of these have other common ions associated with them. So we'll be talking about this a little bit later, but I wanted to show you that there are actual differences in the charges given some of these elements. There's no need to memorize this table. You can always back calculate out of the formula to the name. And if you're given the name and trying to write the formula, the name will indicate exactly what charge is on that cation. So let's get to this. Here are all your common ions that were shown on the previous slide. If you notice, these are the names. So Cr2+ would be read as chromium 2. These Roman numerals have to be written when you're dealing with transition metals. You will never write a Roman numeral when dealing with the main group metal to nonmetal. You will only write Roman numerals when dealing with transition metals to nonmetals. So That's a very good, tricky point that I can ask on a quiz. If I'm giving you a main group metal, no Roman numeral. If I'm giving you a transition metal, you must put that Roman numeral. So Cr2 plus is chromium 2, Cr3 plus is chromium 3. And we can see here lead Pb 4 plus. This is how you write the Roman numeral for 4. So Roman numerals are going to become key. Let's look at how we can input these or use these in a molecular formula and writing the name from it. CuCl2. At this point, there is no way for you to know exactly what the charge is on this Cu. We will talk about this tomorrow, but let me just tell you what it is now. This would be copper 2. So the metal is the cation, our copper is our cation, and in this case it's going to be copper 2. And we'll talk about how that came about tomorrow in class. But I just want to be able to write the name from this formula. So this is copper 2. The anion, we know all we do is drop off the ending. Since it's chlorine, we drop off the ene part and add "ide," and we have chloride there. So in order to make this a full name, we just read off our cation, including the number, and then add the anion, the modified anion. So this would be copper 2 chloride. You have to say the 2 when you're saying this formula. Otherwise, nobody will have any idea what the charge is on that copper. So this would be read copper 2 chloride. Let's go through another example. Excuse me. Manganese something oxide. We have to figure out what the charge is on this manganese. We don't know how to do that yet, but let me just tell you, it is a 2. So this would be the metal is this manganese. I know it sounds very similar to magnesium, but it's manganese. Anytime you have this Mn, it's manganese. This would be manganese 2. And then the oxygen, we already saw how to modify it on the previous one. It becomes oxide for our nonmetal. And so the name would just be manganese 2 oxide. Very simple to go from the formula to the name once we know what the charge is on this metal. We'll learn this, like I said before, in class tomorrow. Now let's talk about one last topic before we finish with this video. How are the strengths of the ionic bonds associated with the size? There's two things we're going to be associating with: the size of the ionic compound and the charge on the ionic compound. So this plot is a really good plot to know. As chemists, we really like trends, and so these are some trends, some nice trends that we want to talk about. Here we can see if we have something that's relatively the same size. So the top row, they're about the same size. The one on the left has a +1 and a -1 charge. So this would be your cation, the blue one. The yellow one would be your anion. If we move to the right, we now have gone up to a +2 and a 2- charge. Still about the same size. The attraction, the strength of this ionic bond increases as we increase in charge. So that's what we see here. We have a +1 and a -1, and we have a +2 and a -2. The strength of the bond increased going from left to right. Great. Let's see how size affects the strength of the bond. Here on the left we have a +1 and a -1. At the top we have a +1 and a -1. You can see that the bottom one is much larger than the top one. So as you decrease in size, you actually increase in the strength of the ionic bond. So this 1+ and 1- is weaker as an ionic bond than the smaller 1+, 1-. So let's see which ones of these are going to be the weakest and the strongest according to these trends. So as you decrease in size, you increase in charge. As you increase in charge, or you increase in strength. As you increase in charge, you increase in strength of the ionic bond as well. So the weakest one on this whole picture would be the 1-, 1+. That's the large one, because it has to be weaker than the smaller 1+, 1-, and it has to be weaker than the larger 2+, 2-, because it has a smaller charge. So this is the weakest one on the plot. The strongest one is going to be your smallest 2+, 2-. How do we see that? This has to be stronger than the small 1+, 1-, because it has a higher charge. And it has to be stronger than the bigger 2 plus, 2 minus, because it's smaller. So that's how we're going to read this chart. And with that, we're going to be talking a lot about formulas tomorrow. We're now becoming true chemists. We're going to be able to use our knowledge of the periodic table, of assigning group numbers and then assigning charges and figuring out what the ionic charge is for each of these metals to nonmetals. And tomorrow we're going to learn how to write the formula and then go from formula to name. So there's going to be a lot of different practices that we're going to be going through tomorrow. And I hope you all have a good night and see you in class tomorrow.